Okay, in this video, we'll talk about another type of improper integral. Right? So in the previous video, we saw that if you wanted to compute an infinite area, right, you could just cut it off somewhere and take the limit as t goes to infinity to compute whatever that area is, if it did exist. In this video, we'll talk about another kind of problem that may happen when you're trying to compute integrals, and it's exactly when you have a discontinuity. Right, so consider the function 1 over x squared, and say you were asked to compute the integral from 0 to 1, right? So that's also an infinite area, but again, we can't really apply the Riemann sum definition here, right? 0 is a vertical asymptote for the function. And so what's going to happen here is we're going to apply the same idea. Okay, so what I'm going to do instead, I'm going to cut this off somewhere, and I'm going to call that t, and I'm going to compute the integral from t to 1 over x squared dx. And, well, this is equal to minus 1 over x from t to 1. And this is negative 1 plus 1 over t. And okay, right? So using the same idea as in the first type of improper integral, I'm going to take now the limit. All right, so let's try taking the limit as t goes to minus infinity. I mean, t goes to 0. Sorry, we're approaching 0 here from the right of whatever this integral was. All right, so as t approaches 0 from the right, is this infinite area going to be something? Well, we can see from our calculations here that, well, this is minus 1 plus 1 over t, and this actually doesn't exist. Yes, equal to infinity. And so using terms from the type 1 integral, we could also say this is divergent, right? Because it doesn't evaluate to a finite number. And so it turns out that if we do have a discontinuity for a function, then this is how we'll do it. If you have, say, an essential discontinuity, which is a vertical asymptote like this, what we're going to do, we're just going to compute the area up to some t, and let t approach that vertical asymptote from the right. Conversely, you can have something on the left as well. Then you do the same thing. You let t approach the vertical asymptote from the left. And in either of these cases, if your limit is a finite value, then we'll say that that is the value of the integral. All right, so that's all this slide says. So f is continuous from a to b. It has a discontinuity at b, but if you take the limit, right, so that's b and that's a. If you take the limit as t goes to b from the left, and it evaluates to something, then we'll say it's convergent. Right? And so same for the other type here. So let's work on an example here it's actually slightly more involved here, and we're not simply asking whether the integral is convergent or divergent, but there's a parameter p in the integral, and we're asking for what values of p is this integral convergent. We already saw from the first example here that when p equals 2, right, so the power of x in the denominator, we already know it's divergent. Right, so how would we solve something like this in general? Well, we're going to do the same thing. Right, we're going to investigate what happens when you take the limit as t goes to 0 from the right of the integral of t to 1. And so I'm going to evaluate the integral separately here. What's the integral of 1 over x to the p dx from t to 1? And this is just a power rule, right? It's going to be equal to, well, what is this? This is like x to the minus p, right? So I can write this as x to the minus p. So this becomes x to the minus p plus 1, right? So the power goes up by 1. And you're dividing by the new power. And so you plug in 1 for x, it's just 1. And then you plug in t for x. And you get this. Oh, but wait, right? It's not just the power rule. We have to be careful here, right? Because this integral actually evaluates to something else if p is equal to 1. Right? If p is equal to 1, that's 1 over x, which means this is the logarithm. Right? And this actually gives us ln of 1, which is 0, minus ln of t. Okay, so what do we have here? So let's see what happens to these expressions, right, as t goes to 0 from the right. It's easy to see that when p equals 1, it's going to be a divergent integral, right? Because when you take the limit, minus ln t, that's going to approach infinity. Right, so it's also divergent here in this case. So we know for 2 it diverges, for 1 it diverges. Okay, so how about this one? This is the general case now for any p. Well, 1 over minus p plus 1, that's just a constant, so I don't care about that. So why don't we look at the limit as t goes to 0 of t to the minus p plus 1 over minus p plus 1. When is this going to exist? And when is this not going to exist? Well, if t were in the numerator with a positive exponent, say t squared over 2, then that would exist, that would just go to 0. But if you had a negative exponent in the numerator, right, then that would actually go to infinity. And, well, that's because you can use the laws of exponents, right? And you have a denominator now that goes to 0. So really what this tells me is that this depends on this exponent up here. If that exponent is positive, right, then we're actually going to get something here for the limit. And that just gives me p is less than 1. In fact, you can also check that if p is larger than 1, then what does that tell you about minus p plus 1? Then minus p plus 1 is negative. And so now you're into the second case here, where you're going to get something that goes to infinity. Right, so I'm not writing this out like proper here. I'm all over the slide here, but I'm going to summarize what we see. Therefore, the integral converges for p is less than 1 and diverges for p, well, it also diverges for p exactly 1 as well as for p larger than 1, so it's p larger than or equal to 1. And that's it. And note here that it's not actually an improper integral for all these values of p less than 1. Right? In fact, it would probably have been more correct to deal with a case where p is negative separately. Because in that case, you could just say, if p is negative, then the integral converges, because it's just going to be an integral of a polynomial. Right, so you could have actually started out by saying that. But, I mean, we see it from this analysis anyway, looking at the terms here. Now, another example here demonstrates something you have to be careful about. And that's when you have a discontinuity inside, right, your upper and your lower limit for your integral. Right, so here it's -1 to 1. So that's kind of like asking what's the net area here. But you have a vertical asymptote at 0. And so what you're going to have to do here is to simply break it up. Compute the improper integral from 0 to 1 first. And then, I mean, -1 to 0 and then 0 to 1. And the computation here is going to be similar, right? What does that look like? Well, ln x dx. So let's do 0 to 1 first. Well, it's positive, so we can just remove the absolute value there, and that's going to be x ln x minus x from 0 to 1. And, well, that's not actually correct there. I should be using limit notation here from the right. Right, so if you did something like this on a test, right, that would be incorrect. Because you have to compute the limit of this definite integral when you have t instead of 0. Okay, and you'll have to do L'Hopital's rule here again for x ln x, because that gives you an indeterminate form 0 times infinity. When you plug in 1, it's -1. And when you plug in t, okay, so now you compute the limit. So that becomes t ln t. And this is actually going to give you 0. Right, so that's now infinity over infinity. Use L'Hopital's rule. It's 1 over t, -1 over t squared. So in fact, that's just -1. And you can do a similar calculation for the other side, on the negative side of this. But, I mean, you already know from symmetry that's also going to be a -1. It's the exact same area, right? You just reflected everything across the y-axis. But yeah, I mean, try it out yourselves. The limit as t goes to 0 from the left now. Have the integral from -1 to t ln absolute value of x dx. Right, and so just to generalize what we just did there, if you have a discontinuity at a point c inside your interval from a to b, then just split up your integral into two integrals that are both improper. Right, and then if they're both convergent, then this whole integral from a to b is also going to be called convergent.